My name is Adina. I'm part of the Psychoinformatics Lab in the Institute of Neuroscience and Medicine in the Brain and Behavior Institute. And today I'm going to give an introduction to DataLad, a software tool that we are developing with a focus on machine learning application. If you want to get the slides, because they can be useful for you to follow the links that I've put in them, I have pasted the link into the chat and you can download them from GitHub. I want to start with acknowledgements, the most important thing first, because DataLad is a software tool that is and has been developed by a large number of people in a large US and German collaboration. One part of that collaboration is here in the FZJ in the INM7, led by Michael Hanke. The other one is at Dartmouth College, led by Jaroslav Eichenko. And I myself am the lead of the documentation project, to which also many people have contributed. We're funded, and I want to highlight our funders and collaborators here. Yes, so I also want to highlight that while I'm giving the talk here today, I'm only here for 2 hours. You can quiz me with any question that you have, but importantly, everything that I'm talking about is already documented in depth elsewhere. So if there are any questions that you have at a later point, then you can find resources to get answers to your questions or to ask those questions to us. The most important resource is the DataLad handbook. You can find it at handbook.datalad.org. And this is a website that is a collection of all of the user-facing tutorials that we have created over the duration of this documentation project. You can find general introduction and information and installation information about the tool. You can find a hands-on introductory tutorial that takes you throughout the basics of the tool. You can find content on advanced things that you can do with DataLad, and you can find use cases where you can read up on what's possible with DataLad. In particularly relevant maybe the use cases that were created in particular for this session today. And if you're not into text-based resources, then we have a DataLad YouTube channel where we upload all of our talks and tutorials. At this point, I also want to highlight that we're recording this talk. And I think that we're only recording what I'm screen sharing. But if you want to make sure that your face is not seen on the recording, then please feel free to disable your video at any point. So just as a disclaimer, we're recording this and we plan to publish it later on our public YouTube channel. Okay. If you have questions over the course of this presentation, because this is a virtual presentation and things are a little bit more complex, if I don't have an audience that I can actually see, then please ask them right away if they are concerning something that I'm currently talking about. You can first write them in the chat. If I don't react, speak up because I'm not having good access to the chat. If you have a specific use case that you want to ask specific questions for, then I'm happy to discuss that at the end of the talk. And if you have questions at a later point, then you can ask all of us, the core developers, and many other people that use DataLad or contribute to it in our Matrix channel or via GitHub issues, where we are very responsive. I also have a live polling system in place to make this virtual talk a little bit more interactive. And I would ask everyone to just grab their phones and scan this QR code or go to this URL. I'm also going to paste that into the chat in a second. And in this live poll, you will be able to answer questions that I'm asking. Let us check the live polling system. I've just started the poll, so you should now be able on your phones or in the browser to answer the questions that I'm showing you. Awesome, that seems to work quite well. I hope the other place that someone is joining from is much nicer than any of the other alternatives, maybe the beach or somewhere. Wow, there are many people here. Okay, cool. Let me get a grasp of the audience that I'm facing today. I would be interested in finding out which institute you are affiliated with, just to get a general grasp. We have sent the invitation to all of the institutes, so it would be good to see who was interested. Cool, it's awesome to see so many institutes represented here. Still giving a couple more seconds. Awesome, thank you. All right. Something else that I would be curious to know is whether you have used DataLad before, or if you haven't used it yet, if you have at least heard about it, just to get an idea of how in-depth and detailed I will talk about certain things. Very nice, thank you very much. And then a last question right at the beginning. Which operating system do you use for work? Linux, Mac OS, or Windows? And that's also relevant for me because this is a tutorial that's meant both as a presentation and as a live coding tutorial for which you are invited to code along. And it helps to get an idea of which operating systems are present here. And it seems like it's evenly distributed. Awesome. Oh, there's someone raised their hand. Please speak up if you want to say something. I got a notification. Egon Zimmerman raised their hand.
No, that was wrong. Sorry.
Okay. Okay, but it works. So you can also raise your hand, then I get a nice pop-up notification. So that's also one way to indicate that you have a question. Awesome. So let me start by explaining the live coding. I have my terminal right next to the slides, and I will later use it to have code executed there. I'm going to do this in a Xterm terminal. So my terminal here is remote controlled. That you won't see me typing. You will see a remote control terminal. But you can code along with copy and paste code snippets. If you want to do this, then you can go, it's a little bit smaller, you can go to handbook.datalad.org again, then scroll down all the way to the bottom of the page. And the last section is the code list from chapter section. And there you want to click on Introduction to DataLad with a focus on ML. And there you can see all of the code snippets that I will be executing, and you can copy and paste them into your own terminal if you want to. Cool. If you want to code along, then you will need to have DataLad installed. And if you want to code along for the more advanced parts in the end, then you will need to have a DataLad extension installed, DataLad containers, and the software singularity. You still have a couple of minutes to do that if you're interested in doing that, because I will now go through the core features of DataLad. So first things first, DataLad is a command line tool. It's available for all major operating systems, so Linux, Mac OS, and Windows, and it's free and open source MIT licensed software. It is built on top of two version control tools, Git and Git Annex. And DataLad, if I want to sum it up in a couple of catchy phrases, allows to version control arbitrarily large content. This, for example, enables you to version control not only code or software, but also data alongside each other. It provides transport mechanisms for sharing and obtaining data, so you can consume and collaborate on data or data analysis as you may be used to in software development. And it provides means to create computationally reproducible data analysis. And it allows you to track and also share the provenance of all digital objects that you create in your research. DataLad has also many more features, but these are the things that I'm going to focus on today. Also, DataLad is completely domain agnostic. It's been heavily used in the neurosciences, and some of the things that I'm showing here will be using neuroimaging data, but it can be used for anything. You can also version control your music library with it, and it is not bound to any specific data type or scientific area or whatnot. So I'm going to quickly give you a run through of all of the core concepts and features I want to talk about. And then I'm going to start with the general introduction with a code-along tutorial for these core concepts. And later I'm going to focus on a concrete and more complex machine learning application. So among the most important things to know is that everything that we do with DataLad happens in so-called DataLad datasets. Those are DataLad's core data structure, and you can create them in as a new directory, or you can transform existing directories into datasets. You can also get them from elsewhere. Once you have a dataset, then it feels like a usual directory on your computer. In this slide, I have included a screenshot of a DataLad dataset, one from the file viewer on the left and one from my terminal view on the right. And this is just a regular directory as you would have typically on your computer. A dataset, as a little bit of technical background, is a Git annex repository. If you don't know what Git or Git annex are, that isn't super relevant, and you won't need it to understand what I'm talking about. But it means what I want to highlight is that it's completely content agnostic, that there are no custom data structures involved that you would need to use, and that those tools, and in turn also DataLad and DataLad datasets, are built for complete decentralization. So with using DataLad, you don't need a central server or a central service. Everything can be hosted on your local machine, on your local private laptop, and that would be enough. Datasets can version control arbitrarily large files. So you can place files of any size into a dataset and save them in order to version control them, and later on save all of the modifications you do to these files. And you can stay flexible in your use of this version control feature. You can decide to use a non-complex core API of DataLad that will help you get started with version control if you have never used a tool like Git or Git annex before, or if you have students that are new to data management. But if you are a Git or Git annex user, then you can also just use pure Git or Git annex commands if you want to, if this is something that you're more comfortable with. A dataset, because it has those version control features, creates a history that you can use and interact with. You can see a screenshot of one view of such a history of a dataset that I've created, and you can see that everything that I've done in a dataset on the right-hand side is summarized with a small change summary of what I've done here, and with an author that created the change, and with a date of when this change happened. And I could also go deeper into this history and see precisely what has been done. This history can be used for various things. It's Git history for everyone who's familiar with Git. Once you have this history, you can reset the complete dataset or subsets of it to a previous state, so you can travel back in time and check out previous versions. You can revert changes that you have done so that you are not happy with, for example, or you can also bring them back. You can find out what was done, when, how, why, and by whom. And that's regardless of if it's your own dataset or if it's a dataset that someone else has shared with you. So everything that has been done in a dataset is transparent to the ones that you've shared it with. You can share the complete provenance history of everything that has happened. And you can identify every file or subset of the dataset in precise versions. This, I will show you later, enables you to, for example, use data in the most recent version, or the version that the data was in 2018, or at another point in time, and so forth. You can consume datasets and collaborate with datasets. So if you have a dataset, then you can share it either on the same compute infrastructure or to a different place, for example, repository hosting services such as GitHub or cloud storage services, and others can take those datasets and either get their data or collaborate with you. And likewise, you can consume existing datasets, and DataLad provides easy updating mechanisms that allow you to integrate changes that the creator of the dataset or collaborator on your dataset has made into your own dataset. DataLad creates machine-readable and re-executable provenance of the things that have been done in a dataset. So what it can do, for example, is to link input code, containerized software environments, and the results of a computation or command execution into a both machine and human readable record that a machine is later capable of re-executing automatically. And it can capture and store the origin of files so that you have both a record of how files were created, or if they haven't been created by you, where they have come from. And DataLad allows for a seamless nesting and dataset linkage mechanism. It's not really straightforward immediately how this can be useful, but there's a glimpse of what it can do here in this slide. It allows you to, for example, create a complete provenance record or complete lineage of, let's say, the raw data up to the published result in a paper without sacrificing interpretability or intuitive structure. And I will later show you in a concrete example of how this nesting can become really useful to create intuitively structured and reusable analysis components. And DataLad is built for integration with all kinds of third-party storages. So even though it is completely decentralized and your local compute infrastructure, be that your private laptop or the JSC, is the perfect place for DataLad to work and for your datasets to be, you can also host your datasets in all major third-party repository hosting services, let's say GitHub, GitLab, Gin, Bitbucket, and so forth, and also cloud storage services, for example, Google Drive, or stuff like the Open Science Framework. Here are some concrete examples of what people use DataLad for. One thing that many people do is to publish or consume datasets via public-facing services, for example, GitHub. You can see in the screenshot a GitHub repository that is actually a published, quite large neuroimaging dataset. I can then get the URL of this dataset, of this repository, clone it, and subsequently I have access to several dozens of gigabytes of data that are shared in this dataset, all publicly available via GitHub. And coincidentally, I will also have access to the complete history and so forth, but I will show that later. Another thing that DataLad can be used for is to create and share reproducible and open science. Here is another GitHub repository, public-facing for everyone, and it says that it shares code, data, and the manuscript for the paper that this DOI links to. It's a paper that has been published earlier this year by us. And if I then clone this repository, again, this can be done by everyone, it's completely public facing, then I don't only have access to the code and data that is shared inside of this repository, but I also have access to the provenance history of everything that has been done. And I can find out what has been done from the raw data to the result that I report in the paper. And this is an example that you can check out on GitHub. It's actually a completely reproducible and dynamically generated manuscript. So you can clone this data set and you can build the manuscript, including freshly generated results from scratch. Another thing that we use DataLad for in the INM7 is for central data management and archival. This is a screenshot of our GitLab instance. And in there we have a collection of all of the large neuroimaging datasets that aren't publicly shared, but that we have packaged up in DataLad datasets. And we expose them via GitLab for everyone to clone. And we actually join them into a so-called super dataset, which when cloned gives access to all of the hundreds of terabytes of data that we have packaged up in the Institute for our data management system. Okay, and now I'm going to demo the basics of DataLad in the terminal. And if you want to, you can go to the shared link and copy paste the code snippets into your own terminal to follow along. Let me see if I get this to work. Perfect. So I've said that you need to have DataLad installed. And here's a quick check of whether it's the correct version. If you type something like this into your terminal, then you should get DataLad with a version number that should be higher than 012. What I'm also showing here is, if you have never used DataLad, is how to configure a Git identity. I will later come back to why this becomes relevant, but this is also a requirement or a configuration that you should do prior to starting with DataLad. So quickly back to the basics. So DataLad is a command line tool. So you have seen that I have used it in a command line with DataLad prepended by some command or a flag, but it has also a Python API. And if I would want to use it in a Python session or in a script, then I'm quickly showing you how you would be able to import DataLad's API, for example, with the following line. And this allows you to use DataLad and its functionality also in scripts. It has a Python API, but it doesn't prevent you from using DataLad in other sorts of scripts. So if you have a MATLAB script, for example, you can still have access to DataLad's functions via system calls, for example. I will start by showing you how to create a DataLad dataset first. That's DataLad's core data structure. And you can create a new dataset that you can populate on your local computer with the DataLad create command. This command only needs a name of the directory that shall be created. So I'm running DataLad create my analysis, and that will create a new dataset called my analysis on my computer. And what you can also see here is that I'm attaching a configuration option that will generate a useful structure in my dataset that is useful for analyses. But I will later explain the details of why I have done this. If I execute this command, then DataLad will create this new directory that I can now cd, so change directory into, and I can check out the contents because the configuration has populated this directory already with some useful things that are nice to have in a data analysis, namely a code directory so that I'm encouraged to place my scripts in there, and some readmes and changelogs with placeholders so that I'm encouraged to document everything I'm doing. If I take a closer look by listing all of the files, so also the hidden files in my dataset, then I can see that there are some hidden directories and files. So for example, the .datalad and the .git directory that show you that there are some version control tools that are working in the background. So great that so many people have already answered that question here. Before I start with the version control feature of DataLad, I would like to know whether you are familiar with using version control tools such as Git.
I'm not too familiar.
Thanks for the feedback. It's fantastic that so many people are using Git. Or have used Git. That's really cool. I will quickly use a minute to explain what version control is for those that have not heard about Git. My go-to example is Wikipedia. If you go to Wikipedia, then that's a collaborative space where people can share knowledge. And you can have an article on Wikipedia and add information to it by logging into your Wikipedia account and then proposing a change to the article by typing your change into a small window and then summarizing that change and submitting it. The article will be updated right away, and it will importantly not change its URL or its file name. So even though if you have edited a Wikipedia article, the article has changed, it will still be the same file name, the same file URL that everyone can access. This is a stark contrast to what is depicted here in this comic, where a document is changed, but instead of saving it under the same name, these minuscule changes are just reflected by more and more complex file names. So this comic depicts a directory that will end up with hundreds of files with slightly changed file names, and each of these files has a minuscule change. In Wikipedia articles, there's a version control system in place that prevents that. At the same time, each Wikipedia article has a history of what has been done to it. So you can go to any history of a Wikipedia article and find out who has added which information at which point. And if you would go to the article of Pope Francis and then add information such as he was a phenomenal strip poker player, then someone else will quickly notice this change, will identify the change that you have made in the history, and is then able to revert that change because he or she were able to interact with the history of the Wikipedia article. So version control is one way to keep things very organized instead of cluttering files with changing file names. You have a linear history of your files with changes that you can use where you can keep track of changes, and you can revert changes or go back to previous states with version control. Now, typically version control is only used for small files, let's say code, let's say manuscripts, but it's important to also apply this to larger files, and that's possible with DataLad. DataLad in principle knows two things: datasets and files. We have already created a dataset, and everything that you put into a dataset can now be version controlled. And it always happens with the same command, and I'm going to show you how this looks like now. What I'm showcasing here first is I will edit one of the README files that is in the dataset. They are already in the dataset and thus are version controlled. And if I execute this command here, then I will just echo an empty space into the README. I'm doing this because I have a remote control terminal, but what I'm essentially doing is I'm just deleting the placeholder contents of that README. I can, now that I've made a change into a file that is version controlled, find out what has changed. The command that lets me do this is, for example, the DataLad status command. This command will report on the current status of the dataset. And if I execute it, then it will tell me that one of the files given to it for version control has been modified, so changed from its previously known state. I can get more details on this precise change by asking Git to report the change to me. If I ask it to do this, then I can actually see the precise lines that have been removed. All of those are highlighted in red, and the line that has been added, this one is green with a small plus. I will also remove the placeholders from the README file that is in the code directory. Here's a summary of all of the modifications that are currently in the dataset. So both the README in the root of the dataset and the README in the code directory has currently lost the placeholders in them. If I now think that's a great change, I want to version control this, then I can use the DataLad save command to save the current state of the dataset. What you can see here is that I'm using the -m, that's short for message option, to attach a short summary of what I have done here. This is a good practice because it helps me to create a nice and human readable history in my dataset that others and my future self can understand more easily. If I execute this, then it will add the modifications that I've done to these two files to my dataset. And that's all that version control is. Something that I want to address here, because version control is so simple that we can now practice good practices, is that the DataLad save command saved all of the modifications in the dataset. And that's something that you want to be mindful of if you have several changes in your dataset. I'm going to do two changes now. First of all, I'm going to add something to my README. You can do this too with an editor of your choice. And the next change I'm going to do, so here's the difference that I've introduced. And the next change that I'm going to do is I'm just going to download a file from the web. It's a funny comic that I like and add it to the dataset. if I then query the dataset state, you can see that there are two modifications in my dataset. Now, what I want to draw your attention to is that these two changes are very unrelated to each other. There is a README change and there is a new file. And I wouldn't want to save them into the same commit or into the same save message because they don't have much in common. And I'm always inclined to do incremental changes that make sense when reverted as one unit. If I ever want to revert that README change, then I want to make sure that when reverting this one save operation, I don't also want to get rid of the file that I've added. And one way to only save a single change or some changes in a dataset is by adding a path to the DataLad save command. So if I'm adding README as a path to the DataLad save command, I'm making sure that I'm only adding something to the README, and then I can do another save. In this case, I don't need a path anymore because there's only one change left to add the additional file that I have included here. So procedurally, version control has gotten really, really easy. If you're used to Git, then you can see that I'm skipping a couple of Git commands or combining a couple of Git commands all with the DataLad save command. You just need to add a change to a dataset or modify a file that is in there and then save this change with a meaningful commit message. It is advised to save only meaningful units of change and to also attach a helpful commit message to it. And because you can save anything that is in your dataset, this means that you can also version control data. So if you have just acquired a neuroimaging study, then you can take all of these gigabytes of data and just run a DataLad save on them to version control them and save them into your dataset. Now, the dataset has started to get or to build a dataset history. And I'm going to demonstrate this here by showing you the history of, for example, a single file in my dataset, for example, the README. And you can see here, this will be familiar for everyone who's worked with Git, and I'm going to quickly walk through what this is for everyone who's new to Git. You can see here a log of everything that has been done to a single file in my dataset. Each of these entries have certain elements. One important piece is the so-called commit hash. That's a hash or a 40-character string that uniquely identifies each change or this particular change. We have associated it with an author and with a date and a time. And the author, so my name and my email address, is where the git config command has come into place. So I can associate the change that has been done with the person who did it. And you can also see that there's a commit message that summarized what has been done. I can now interact with this history by, for example, checking out previous states of the dataset. So if I identify a precise change with a part of this hash, I can take a look at the contents of the README file, and you will see that the original placeholder that I have changed is now back. And I can also move forward in time again by going into the most recent state of the dataset again, and then I have the contents of the README in its most recent state back. One thing that is useful to know is where files came from. So you have seen that I have added a webcomic from the internet. And if I would share this dataset with you, then you will just find this webcomic, but you would have no idea where it comes from. DataLad has means to record the origin of files in a dataset. And I will show you the command that does this right now, and I will later come back to tell you why this is particularly helpful. So what I'm doing here is I'm hiding a little Easter egg by taking another webcomic, another XKCD comic, here's the URL, and downloading it and saving it under the name .easteregg, so it's a little hidden file. And importantly, I'm not doing this with the wget command as before, but I'm using a DataLad command that is called DataLad download URL. I can add a commit message to this command, and if I execute it, then DataLad will go to the URL register the URL it finds there, downloads the file, and saves it under the commit message that I have given to it. And if I open up this Easter egg now, then that is on my screen here, I have a nice little comic. And I will come back to why this is a particularly helpful command in a couple of minutes. So as a quick summary for now, local version control is really easy. DataLad creates an empty dataset, and there are configurations that are useful, but the details of which I will tell you more about in a while. A dataset has a history that can be used to track files and modifications, and it is a git log that you can explore either with the git log command or any tool that visualizes git history, for example, Tick. If you want to save a dataset state, then you use the DataLad save command. And if you attach a commit message, then you can summarize the change for future you and for others to create a nice dataset history. DataLad download URL is a command that obtains web content and records its origin and also saves the change. And DataLad status is an important command that reports the current state of the dataset. You should make sure that you would always return a clean dataset state after dataset status. That's a good practice to have no untracked modifications of files. So with these three commands, essentially, DataLad create, DataLad save, and DataLad status, you have come from no version control to really easy version control of any kind of file. And now I'm going to go to the next feature of DataLad, because version control is only one aspect of data management. But first of all, cool. If there are any questions, then please let me know. Else I'm going to go further about consuming datasets. I've shown you that a dataset can be created from scratch or in existing directories, but you can also install it from URLs. And I'm going to show you how to do this by going out of this directory that I've created here and cloning a dataset that is available on GitHub in the DataLad dataset collection. If I clone a dataset, then here is what it looks like. I can see in my screenshot here that there are a lot of files immediately after cloning, and you can browse the file names. But that is an incredibly fast operation, and the resulting datasets is really lean. This is the case because in all likelihood, whenever you clone a dataset, for most files, there is actually no file content, but only what we refer to as metadata, so file names and availability of where this file can be retrieved from. So I can install, let's say, a neuroimaging dataset that is several dozens of gigabytes large, but if I have it on my computer and then use the disk usage command with the SH flag to report back its size in human readable measures, then it's just a fraction of its total size. And if I then want to have file contents in a dataset, then I can retrieve them on demand. So whenever I actually have to use them with the DataLad get command, this will then retrieve file contents if I need them. This one thing that this is useful for is that I can now have access to more data than my computer has disk space for. Here's an example of some large neuroimaging datasets that we use it for. Let's say the ENKI dataset that takes up about 1.5 terabytes of space on our cluster. But if I have it just cloned, then the directory will be only 1.5 gigabytes in size. One of the largest neuroimaging datasets, the Human Connectome project dataset, it's 80 terabyte in size. So terabyte, 80 terabyte, let that sink in, and contains 50 million files. And even though it is a substantially large directory with 50 gigabytes on a local computer, it's still only a fraction of the size, and it gets me access to all of the data that is in there. So in principle, it's plenty of data, but little disk usage. I will show you that in this directory that I've just cloned. So that's a directory that is filled with machine learning books. And you can see that there are all of these PDF files in there, not that many, but a few. And if I want to actually read some of these books, I can get them with the DataLad get command. In this case here, you can see me getting all of the books that start with a capital D. So you can not only obtain individual files, but you can also obtain complete directories or everything in the dataset. You can make use of globbing if you want to. So what is even better than being able to get content on demand for a disk space aware computing workflows is that you can also drop data if it's not needed anymore. So after you have, for example, completed your data analysis and you want to free up disk space again, then you can use the DataLad the DataLad drop command to get rid of the file content of the file. Afterwards, you will still have what we refer to as metadata. So you have still the file name and you can retrieve it on demand again, but it doesn't take up disk space on your computer anymore. And this allows for disk space aware computing workflows. So something that you can do now is you can install your input data that can be terabytes large. Then you can get the data that you need, because in some computations you may not need all of the data of a data set. You can compute your results on the obtained data and then afterwards drop the data so that your disk space is freed from the input data that you currently have no use anymore. And you can extend that also potentially to things that can be automatically recomputed, and I will show you later how this is done. Something that I wanted to show you still is how DataLad drop behaves with the two files that I have added to my dataset with the two comics. And I want to do this to highlight the difference between the DataLad download URL command and simply saving a file with no origin recorded. If I drop the Easter egg file that I have downloaded with DataLad download URL, then DataLad will make sure that it can retrieve the content on demand. So it checks the URL that is registered to see whether it can get it back. And only if it determines that this file can be retrieved, it drops the file content. If I want to drop a file where I don't have a second or third origin recorded, then DataLad will refuse to drop this file unless I force it to, simply to safeguard losing access to files that can't be obtained from anywhere else. Cool. So if I have dropped something, some file contents, then you will see that tools will not be able to open it up anymore. But you can retrieve these files on demand. And now DataLad will reobtain this webcomic and it can be opened again. And yay, I have a webcomic again. Cool. Now, the reason that this works is a little bit technical in nature, but I want to give you a quick explanation of why that is. So data that you put in datasets is either stored in Git or in Git Annex, so in one of the two version control tools that DataLad builds up on. By default, everything that you put in a dataset is annexed. And that means that Git Annex hashes a file. This ensures file integrity because it hashes the content to uniquely identify that file content isn't changed. And then it moves the data into a dataset annex. It then only commits the identity hash and location information into Git, which is a really small piece of information, typically only slightly more than 100 kilobytes. And everything in the annex is then managed with Git Annex. This is because Git isn't capable of handling all types of files well. So while Git can handle small files, Git really barfs if you put too many or too large files into it. Git Annex, on the other hand, handles all types of files very well. Another advantage that Git Annex has is that it allows to share files if you want to share them. So while when you share a dataset, everything that is placed in Git is shared right away with everyone who has a copy. You can keep annexed files private on a per file level basis when you share the dataset. Now, all of this is a little bit technical in nature, and there's no need to understand the precise reasons for that now, but I'm saying that to prime you for differences in behavior that you see in datasets for files stored in Git versus Git Annex, because these two tools handle files differently. Files that are stored in Git are easily modifiable, for example, the README files. Well, files stored in Git Annex don't have write permissions anymore to ensure their file integrity, and they need to be consciously unlocked with a specific command so that they can be modified and changed in a new version. I will show you later how this is not a problem at all when you're actually working with the data. And Annex contents are not available right after cloning, so this is everything that you get with a DataLad get. Only the content that is stored in Git is available right now. Now, if you have a data set and you have Annex data there and you want to share it with someone who is not on the same compute cluster, it's actually not a difficult thing, but you do need to make sure that you share the Annex data consciously with someone else that you want to share your data set with. You can interface all major repository or storage providers that there are. So if you're using Dropbox anyway, or if you're using Google Drive anyway, then you can, then DataLad and Git Annex have means to easily, with a few commands, interface all of these services, publish your Annex data there, and make them available for others that have your data set. And everyone who uses your data set doesn't really care or know where data comes from, because everything is secretly handled underneath the hood, and everyone gets the data wherever it may be stored with a DataLad get. It may be relevant to modify whether files are stored in Git and Git Annex, and there are easy means to do so. Run procedures like the configuration that I've used applies configurations that are tuned to specific use cases. So the Yoda procedure, for example, will make sure that anything that is in code, so all of your scripts, are not annexed and thus shared right away and easily modifiable. You can also create such procedures and distribute them in your institute so that others can have your configurations. You can write configurations yourself, and there are rules and examples and tutorials in the DataLad handbook. And you can also do it on a command basis by, for example, attaching the option to Git to DataLad save. All right. I hope that I haven't missed questions in the Zoom chat. If so, please let me know by speaking up. Else, I'm going to continue with the feature of dataset nesting. DataLad has a seamless nesting mechanism that allows you to link datasets in subdataset, superdataset hierarchies. And here you can see how a raw dataset is linked to a preprocessed dataset that uses the raw data as its input, which in turn is linked to an analysis dataset that uses the preprocessed data as its input, which in turn is linked to a paper dataset that uses the analysis for reporting. And if I then share the paper dataset, I can consciously decide that I can share the entire linkage, the entire history or track of datasets that can bring a reader from the published results that I have to the preprocessed or raw data, so that they can make sure to see the entire evolution of everything that has been done. One thing that nesting is good for is that it overcomes scaling issues with large amounts of files. If you've used Git, then you may know that Git struggles once datasets gets too large. But by nesting and being able to recursively operate seamlessly across dataset boundaries, you are able to basically go however large you want to. Here's an example of the Human Connectome project dataset that we're packaging up, or that we've packaged up in a dataset. You can see that I'm running a recursive status query from the top level dataset throughout all of the sub datasets that this dataset has. And I'm capable of applying this status recursively throughout all of the datasets. There is so from my feeling as a user, it's a mono repository instead of several ones. And with this, I'm capable of version controlling almost 80 terabytes and 15 million files, more than 15 million files easily. The other advantage that dataset nesting has is that it modularizes research components. It makes it not only transparent of, let's say, here's the raw data, and here's the preprocessed data that originated from the raw data, but it also makes it easy to reuse individual components. So you can see in this graphic that the preprocessed data is kept as a modular dataset that can be installed by 2 separate analyses so that the reuse of the preprocessed data is maximized. And what this can also help is with access management. So if you don't want to share the raw data when you publish your paper, say, then you can not share this individual component in your data analysis evolution, but everything else. I can show you how this is done by starting to configure or to prepare the data analysis that I'm showing you in a couple of minutes. And what I'm doing here is I'm installing a dataset that I have published on GitHub. And importantly, I'm using DataLad clone not only with the URL, but I'm using DataLad clone with the -d, that is short for dataset option, that points to the root of the dataset that I'm currently in. What this does is it downloads or clones the dataset from GitHub, but it registers it in its most recent version into the dataset that I'm currently using. So now I have a nested set of datasets, and my super dataset, my analysis, has registered which version of input data I have just installed and where this input data came from. You've also seen that I've added a path to the DataLad clone command so that the DataLad clone command does not create a directory iris data, but actually saves it as input data to make it obvious for everyone I'm sharing the dataset with that this is the input data that I'm using. All right. So as a quick summary up to now for dataset consumption and nesting, DataLad clone is the command that installs a dataset on your local computer. And you can install datasets on their own from local sources like paths or URLs. But you can also install dataset as sub-datasets within existing datasets with the dataset option. When you obtain a dataset, then you only get small files that are kept in Git and metadata about file availability. Actual file content or annexed file content is retrieved via DataLad get on demand. Datasets preserve their history, and while I have installed the sub-dataset inside of an existing dataset, my super dataset has now only recorded the version state of the sub-dataset, and the sub-dataset still has its history. There's someone who was too shy to ask something about version control. If that question is still relevant, then please speak up. You can't say you're too shy, even though I put it there.
It wasn't me who said that, but I still have a question.
Sure, go for it.
I don't want to overrun anyone. We also, or someone discussed it in the chat regarding Word or Excel, and then Michael Hanke replied that it works with binary files or so, but I don't really know what that is. So maybe you could explain how that would work.
Sure. So there's an important distinction between binary files and non-binary files. You've seen that the README file, I was able to git diff and get a precise difference of the change that I have done. This works because a README file is a text file and not a binary file. Binary files are stuff like anything that's not a text file, including, let's say, Excel spreadsheets or Word documents. This makes it so you can still version control all of the binary files. The thing that you're not easily capable of unless you install Git extensions is to visualize differences that you place into these files. And if you can, I would always advise to use text files for everything. So I'm using LaTeX files, which are text files for my scientific manuscripts. I'm not using Excel or Word documents, but let's say Markdown files or TSV files or CSV files, because there I have this option of visualizing the differences nicely. Does that help?
Yeah, I think so.
Okay, cool. There's another question about consuming data sets. Please just speak up and ask your question.
Hi, Felix.
Hi, Felix.
My question is, when I have, let's say I have 2 data sets that I created, or 3, and then I think, okay, it would be much better if I combine them in a super data set. So not going from a large one super to then integrating them, but afterwards saying, okay, I want to combine them. Is that very complicated, or should I start over, or what would you recommend, just in general?
Let's see whether I understood your question. So you have 3 data sets and you want to have them in a single data set.
Yes, I want to recombine them, or to
without nesting.
Yeah, or nest them, or afterwards, because to organize it better.
So you can always nest them afterwards. That's not a problem at all. You can also you can just do it in one data set. You can do a DataLad clone and then install all of the other 2 data sets as nested data sets. There's also a DataLad copy file command, which you could use to transfer all of the files into your other data set. But nesting is generally a really nice and fast way of doing that. And you could also move the data sets into each other and then save it to register it as a sub-data set. So all of that is possible.
Okay, what would you recommend for better overview? I think nested is my feeling, but
I like nesting because you will make sure that you preserve all of the version history of all of the files. So if you have an extensive history in the data sets that you've created and then you later attempt to combine them, then I would always go for nesting, because that makes sure that the files in your data sets all have their individual version history. But if it's something that you've just created and then you have a single entry in your commit history, then you could also go for, let's say, DataLad copy file, which transfers the file but not its history into a data set. I would go for nesting, but yeah.
Perfect, thank you.
Cool.
I have a very basic question, sorry.
Yes. No, don't be sorry.
I'm not sure if I understand the difference between a super data set and a sub data set. Could you please explain it?
Only difference is, so any file can be both a super data set and a sub data set. Any data set that has a registered data set inside of it. So let's say the my analysis data set and the input data set. That the upper level data set, my analysis, becomes a super data set simply because it has another data set registered inside of it. But that's just a naming convention, so to say. There's not that much that is actually meaningful about the distinction between the 2 things. It's just that a data set that has another data set registered inside of it gets an entry about this data set and the version state of this data set. And if I then would take my analysis and install it again as a sub-data set into, let's say, a paper data set, then my analysis data set will be a sub-data set of the data sets I've installed it to, while it is a super data set if you take the perspective of the input data.
Okay, so just to check if I understood correctly, so the super data set would be like the parent folder, and the sub dataset would be like subfolders inside the super dataset or something like that.
That's a good way to conceptualize it. Doesn't necessarily need to be like the parent folder. It can also be several directory hierarchies up, but it's the dataset on top of another dataset.
Okay. Okay, cool. Thank you very much.
Cool. Thank you. Okay, so now I can introduce the topic of reproducible analysis. And that's something that I really enjoy about DataLad, because I know about myself that my past self is the worst collaborator. I don't answer to emails when I want to find out what the hell I had been thinking when I did a particular thing in, let's say, a data analysis. And DataLad has means to make data analysis very intuitive, transparent, and automatically reproducible. I will start this section by giving you a short overview of some of the recommendations or principles that DataLad provides for data analysis on the next 2 slides. One a general advice for data analysis is that everything in a dataset should be kept very clean and modular. And that's related to the nesting feature that I've talked about. If you do a data analysis, then your analysis should be, while you do it, a super dataset, and every component that is a standalone component, let's say input data, should become a sub-dataset so that you can not only link those two components, but also intuitively identify them. It is then important to keep this modular structure clean by not touching or modifying the installed input data, but any results or computations should be saved in your super dataset and not in the installed input dataset. I have these two graphics that display this for one on the left side for the entire evolution of a data analysis from raw data to paper, and on the right hand side from the directory structure perspective of the super dataset, where you have a code directory in which you place your scripts, and the input directory then is an installed dataset that is kept clean, and you will put your outputs not inside of the inputs sub-dataset, but inside of the super dataset if it fits. It's the difference if you have many files that would be too large for a single dataset, but in general, do not override or change an installed sub-dataset with input data. Second thing that's very important in order to keep your analysis portable and to share them easily with others is to keep super datasets self-contained. If you write a script, and I have an example of that in a second, then you should only use relative paths. That is a path that starts relative from the super dataset, and not an absolute path that would include everything on your local computer from the start of your file system. So on Linux, like home, user, and then, because an absolute path would make your analysis not portable. Everyone who would try to execute your scripts would fail to find the path on their local computer if they would rerun them. The next thing to make data analysis as transparent and reproducible as possible is that everything that is done in a dataset should be recorded. It should be recorded where sub-datasets come from. It should be recorded where individual files came from, if you obtained them from web sources, for example. And it should be recorded how a particular result came to be. And I'm going to show you how this can be done with DataLad in the next code section. So you've noticed that I have created this my analysis dataset, and what I'm doing now is to perform an actual analysis. This is only a simplified example, and I will do a more complex machine learning example soon. This is just an example that exists to start with general concepts and commands. What I'm currently doing here is I'm creating a code script for my data analysis. This script is verbatim taken from k-means classification tutorial with Python on the iris flower dataset that coincidentally is the data that I have installed as a sub-dataset. There is nothing spectacular that's happening here. I'm sorry for the big code block that's written into the terminal, but everything that this script does is it loads the input data. You can see it here, referenced as a relative path. It plots the data. You can see that it then saves this plot also as a relative path in the super dataset, not in the input dataset. And then it trains a k-nearest neighbor classifier and saves the prediction into the super dataset as well. If I execute this code section, I have to do this because I'm remote controlling a terminal. You could just do this in a editor of your choice and then see what has changed. You can see that I have actually written the script into a code directory, into the code directory under the name script.py. Another thing that I've forgotten is this script also exemplifies how you can use DataLad in Python scripts. It's superfluous for this example, but I've included it just for you to have an example where you have actually seen it, how its Python API is used. So you can see that here I'm importing DataLad, and then I can make sure that the data is obtained, the data content, before anything is done with the data. And that's just as an example of how the DataLad API can be used in Python scripts. Now, the first thing that I'm doing is I'm saving this untracked script. Apart from commit messages, I can also use DataLad save to apply a tag to state of the dataset. A tag is a Git concept, and it's just an additional identifier that can be used to identify a specific commit. And in this case, I name my tag with the version tag option ready for analysis, because after I have the script, I'm ready for analysis. That makes it easier for me to later identify the stage in the dataset. Importantly, I will make sure that I have a clean dataset state, because the command that I'm going to run next depends on a clean dataset state unless I use specific options. What I'm doing now is I'm executing a DataLad run command. So I'm printing it into my terminal right now, and I'm going to explain what this command does in this graphic. DataLad run takes any command. In this case, the command that I'm giving to it is how I would execute my Python script from the command line with an invocation of a Python interpreter and the path to the script. DataLad run will then execute this command, and it will recognize or record everything that has changed in response to running this command in my dataset and saving that under the commit message that I'm specifying here. And that's a very easy way to associate a command execution together with the results that it created. You can also see here that I'm specifying some optional flags. One is the input data. The input flag makes sure that any data specified in this flag is retrieved prior to computing the command. So I can make sure that the DataLad run command has a provenance record of the data that is required for it in order to run. The output flag is not immediately useful, but it will make recomputation easier later on. And I will show you that also in a second, but first I'm going to run the script. So the DataLad run command now makes sure that the inputs are available and gets any inputs that I hadn't yet retrieved. It then executes the script. It runs really fast now, and it computes these two outputs, the pairwise relationships, PNG, and the prediction reports, and saves them under the commit message that I've specified in the dataset. This has resulted in a run record in the dataset history, and the run record is everything that you can see between those boundaries here. It's not particularly human readable, but it is a machine readable record. And I will now show you how this can become useful by showing you what can be done with it. In order to do this, I will clone the very same analysis dataset that I have just shown you here, because a while ago I created the same analysis and I published it to GitHub, so that I can now go to my GitHub account and clone this very dataset. If I then use a second DataLad command, a command called DataLad rerun, I can identify the commit hash that is associated with the run record. In this case, I already know it and I've included it here, and give it to DataLad rerun. Then DataLad will take the machine readable record that is included in the dataset history, obtain the data that I specified as input, rerun everything that has been done in this run record. It will unlock all of the outputs that I've specified to recompute and modify them should they change. So now I was able to obtain an analysis and to have a machine figure out what has been done to obtain a particular result and automatically redo this. This is a very, very powerful feature that can help to make your data analysis very easy to redo for others. And everything that I have done now is completely transparent. So I can inquire one of the results that is now part of this data set about where it actually came from just by taking a look at its Git log. And you can see now that the first time that I've created this was in May, and from this run record, and now I have redone this in October again. However, this is not all of the provenance that I could possibly attach to a computation. Because especially if the software requirements of an analysis get more complex, I could share data and code with you, and you would still not be able to reproduce what I have done simply because you lack the appropriate packages. If you have tried to run this on your local computer without having the Python packages it required installed, then the command execution would have definitely failed. So an important piece of provenance for every data record should be software. And DataLad has means to also attach software environments to datasets and then execute all of the commands that are given to a run record inside of the software environment. The way that this works is by attaching a software container to the dataset. So a software container is a useful invention that is similar but more lightweight than a virtual machine and allows to wrap a complete software environment into a single file. And there's a DataLad extension that is called DataLad Containers that enables DataLad to work with software containers. So the first thing I'm doing here is I'm going to add a software environment into my dataset with the DataLad Containers add command. This command takes a URL to, I'm sorry, there's a hidden character somewhere in the code that I'm pasting that I apparently didn't fix. What this command does is it takes the URL that I have given here. In this case, it's a URL to Singularity Hub, and it retrieves the container image that I've deposited here. And it saves it underneath the name software, it's an arbitrary name, in my dataset. You could also register a container from, let's say, Docker Hub, and also from local paths. So if you have created a container locally, you can add it from a local path as well. In general, though, if you push it to a container hosting platform such as Singularity or Docker Hub, then your software environment will be available to everyone you share your dataset with. So after I have registered my container, I can rerun the analysis inside of the container, also in a re-executable provenance tracked way with the DataLad Containers run command. This command works just like DataLad run, but it takes the additional option of container name, where you need to specify the container that you want to run. That's useful in the case of several containers in your dataset, so that you can precisely specify which software environment it is that you want to use. And if I execute this, then the exact same analysis is redone, but this time inside of the software environment that I'm sharing in conjunction with data and code in this dataset. So just like DataLad run, DataLad Containers run links data, code, command execution, but also now software environments to a data analysis. So as a summary, DataLad run is a useful command that records a command and the impact, so all of the files, all of the modifications that it results in the dataset. You should use it in a clean dataset because it saves everything that results from this command, but there are options to do it also in unclean datasets, and you can take a look at the DataLad handbook to find out about this. Everything that is specified as input is retrieved prior to the command execution. If you have several inputs, then you can use one input flag per input. And everything that is specified as output will be unlocked for modifications if the command is reran. So it's a useful thing if you want yourself or others to be able to quickly recompute everything with a rerun command. Else the annexed files may want to not be modified right away. The DataLad containers run command comes from the extension DataLad containers and captures the software environment as additional provenance. And this is an incredibly powerful feature because it ensures that computations are ran in the desired software environment. You can use it with Docker containers and with Singularity containers. And DataLad rerun, finally, can automatically re-execute run records later. Okay. Ah, I'm sorry, I forgot. Is there a remaining question about Git annex? Okay, great. Is there any question about reproducible execution? Cool.
Yeah,
Then
so I might have.
Oh, yes,
sorry,
please.
I wasn't fast enough. So you presented the DataLad run command,
Yes.
and then you would basically do one step of the analysis at a time. But usually you have like a lot of different steps in the analysis.
Definitely,
And
yes.
so is there a way to somehow integrate a lot of different steps with a workflow tool, for example?
So you will see an example of that in the next demonstration that I'm doing. But to take a little bit of information from the chat already, so DataLad is not a workflow manager. So you can't specify or cherry pick, let's say, specific run executions, only a range of run executions. So you can re-execute more than one run record. You can execute all of the run records if you want to, or a specific set, but they are always executed in the order that they have been executed in your dataset history. I will show you that and also how it can be used productively in the next demonstration. But I think Michael has already posted a GitHub issue that highlights our development goal of maybe integrating SnakeMake into DataLad so that more workflow management features can be used.
Yeah, that's great. Thanks. I'm already reading the issue.
Okay, cool.
Thanks a lot.
No worries. Okay, now everything that I've shown you was incredibly simple, and I fully acknowledge that that isn't typically how data analysis goes. So you're not just getting a script from somewhere and it works magically at the first try. And it's usually not the case that in machine learning you have a perfectly trained classifier in the first iteration of your analysis. So what I now want to demonstrate here is a slightly more complex example. It's still a tutorial, so it still doesn't incorporate all of the times that, I don't know, code scripts fail or something, I hope at least. But it showcases a more complex workflow and also related to the last question that I got, how you can make DataLad, even though it's not a workflow manager, or re-execute a range of analysis steps to work reproducibly and productively. Yes, there was another question, I think.
Sorry, I have a question in between on the containers. Because you nicely showed how to run such a container, you didn't tell us how to build such a container. So that's the one thing. The second question, not to the containers, but to the input and output statements. Say I have an analysis producing hundreds of files. And so do I have to specify beforehand these hundreds of files by hand, or is there a command summarized automatically for me?
Very, very, very good point. So first of all, the output flag isn't required. You can just not specify it if you don't want to. But you don't need to know, and you don't need to know in advance which outputs you produce, because everything all of the outputs will be saved, even if they aren't specified as outputs. The output flag is only useful for rerunning the command later on. If you have any rough idea, and that idea can be as rough as in which directory these outputs are produced in, you can just use globbing or any more general file path that, let's say, either points to the entire super data set or the directory in which you place your outputs, and then just specify everything that will happen in this directory. So you don't, so let's say your hundreds of files are saved into a directory called output. You can specify -- output and then a path to your output directory, and that would result in this in a perfectly valid specification. Does that help?
Yes, thanks. That made a lot of sense. And the second question was about how to build the containers.
Right. So I don't have a tutorial on how to build containers included in this workshop, but there is a little bit of information in the DataLad handbook. Personally, so the containers that I've used here are very simplistic. And I've described how I've built them in the DataLad handbook. There's a section on containers run that has a hidden section that you can expand, where you can take a look. The container recipes are also public on GitHub, so you can redo them. And there are many tutorials that show you how a container can be built. But it's also important to know that there are many pre-made containers available. So there are many registries. You can find them in public GitHub repositories. I don't have a link out of my head right now, but there are collections of useful pre-configured containers that, for example, are specifically tuned for machine learning analysis and then contain all of the Python libraries that you may need and so forth. So while making a container is not like, so it will take you probably more than half an hour if you start building your first container. But it's also not an impossible task, and there are many resources out there to help, and plenty of containers are already in existence, and you can just pull them from Singularity or Docker Hub because they've been shared by other people for you to use. So that wasn't entirely the answer to your question, but I hope nevertheless soothing information.
That makes sense. All clear. So, understood. And you point me to the resources that will be sufficient. Thanks a lot.
Yes. Later on, I can add a link to the GitHub repository that holds it, but it's a very simple container. Okay. So unless there's another question, I will demonstrate a machine learning example that is a little bit more complex than the simplistic script that I've just executed. So in this analysis, I'm taking, I'm doing an image classification, and I'm using the ImageNet dataset. That's a subset of the ImageNet dataset. This dataset has categories, 10 categories of files. And I will train different classifiers to classify the category that a specific file belongs to. First, I will prepare an input dataset as a standalone component. Then I will configure and set up an analysis dataset. I will prepare the data as a first step in the pipeline. I will train different models and evaluate them, and then I'm comparing different models, and then I'm going to repeat all of this after updating the data and pulling in updates. So what I'm doing first is I'm creating an input dataset. I'm just calling that ImageNet because that's the dataset that I'm using. And then I'm downloading input data. The ImageNet dataset is published as a Amazon S3 bucket. And therefore I can take this URL here and get an archive, a zipped archive of all of these datasets. What I'm doing currently takes a little while because I have to download all of this data first. So I have some time to explain what this command actually does. So the command is a little bit complex that I'm using here, but in essence, it's a DataLad download URL command. While we were writing this tutorial, we found out that there was a bug that we safeguard with this configuration option, but the next release of DataLad will make that superfluous. And we use DataLad download URL to download this archive together with this commit message. And we're using the --archive option because it is an archive. And what this option triggers is very useful feature where DataLad will not only download and save the archive, but it will also unpack the data inside of the zipped archive. And importantly, register the archive internally as a separate data source. So the zipped archive is hidden or stored inside of your dataset in conjunction to the unpacked data. And if you drop the input data, or if you drop the unzipped data, the unpacked data in your dataset, and then would want to reobtain it, the first data source that is registered as backup of where to get data is actually the zipped archive that's still in the internal workings of your dataset. And only if that archive is dropped as well, the complete archive from Amazon will be re-downloaded again. And currently you can see that we have downloaded the archive and it's already saved, but it is now initiating what is called a special remote. That is an annex term for storage locations for annex data inside of the dataset. And once that is done, we're able to use this data. And I'm going to take another sip of water while we wait. Cool. So now you can see that we have processed 13,000 files. And I can then go on to, so just to summarize that, I have prepared a standalone input dataset, and I've added data with the DataLad download URL archives command, but you could also just download the data and then save it. So if you have something that's not available on the web, add it to your dataset, save it, and even though there's no origin recorded, maybe because it doesn't have an origin, you have the same result in input dataset that you can install into your analysis. So next I'm going to create my analysis dataset. I'm going to know what I'm going to use this dataset for my machine learning project, and therefore I'm able to apply a couple of configurations that I find useful. One thing I'm doing is the text to Git configuration. That's a configuration that will place every text file into Git, regardless of where it is in my dataset, so that everything is available right away and modifiable. And I'm using the Yoda procedure again to apply the useful structure with default files for documentation. Next, I create an input directory that I call data, and then I'm installing the input dataset that I have just created as a subdataset into my analysis dataset. Once this is done, this is how the directory hierarchy in my dataset looks like. I'm only showing you the directories, not the files, because these individual subdirectories here have thousands of files in them. And the ImageNet dataset is structured as follows. It has a train and a validation set, and each of these sets has 10 subdirectories in them, and each subdirectory is one class of images. Let's say, for example, a cassette player or a golf ball. One thing that I'm also doing to prepare a nicely configured dataset is I'm going to add a git ignore file. That is something that people that use Git will know about. It's a file that you can use to keep files out of version control. And I'm doing that because I'm executing Python files that create caches that I don't want to have version controlled in any way. So what I'm doing, I take another download URL command, and then I point it to some of the useful shared templates for gitignore files. In this case, it's one that is made for a Python project, and I save it as a gitignore file. Next thing I'm doing is I'm again registering software. I have again made a container to do this that contains all of the Python packages that I'm using for my analysis. And I'm registering it again under the name software, but that's an arbitrary name. And again, I have pushed that container to Singularity. That's my standard workflow. I locally build a recipe in a Git repository. I publish that Git repository to GitHub. I point my account on Singularity Hub to that GitHub repository because that takes care of building the container for me. So it saves me time and compute resources on my local computer, and it makes it available for others. And then I can take the Singularity Hub URL to really retrieve my container, and others can retrieve the container as well. And we're almost done, hopefully. That's a slightly larger container than the one before. Cool. The next thing I'm doing is I'm adding my first script into the dataset. This script will prepare the input data by associating the file names with the label that denotes the class of the image. I'm limiting, for the sake of time, the analysis here to 2 image classes. So the only thing that this script does really is it takes every file it finds in one directory, this one, and labels it golf ball, and it takes all of the other files that it finds in these directories here and labels them as parachutes. Again, this is also something that can be done in an editor. I'm just printing it to the terminal in this here document in order to have a remote control terminal during my presentation. A DataLad status reveals that this is now an untracked script, and I can save it. And I again add a version tag so that I can identify this state later on. And what I can do now is a DataLad containers run command that takes the script and applies it to the input data so that I have CSV files that contain the labels of the file names that I have. For the sake of time, I'm using the runtime max annex jobs configuration here to parallelize the retrieval of files. This way this way I don't have to talk 3 minutes, but only a single minute while this command does its thing. It's a couple of thousand files that are retrieved right now from the input dataset into the local dataset. You can see that I have specified the different inputs, so all of the relevant directories in train and validation as a separate input flag. And you can also see that I'm specifying the outputs precisely here, the 2 CSVs, because I know from the way that I've written the script where the results are saved under. And once the files are retrieved, this command will run the script, produce the CSV files, and save them in the dataset. I also want to thank Benjamin and Michael, who are developers. So Michael is my boss, and Benjamin is a software developer in our team, for answering all of the questions in the chat, because I would have no way of monitoring that. So to go on in my slides also, I have added a script for preparation. It labels train and validation images, just the CSV files, and I execute the preparation of the data in a DataLad containers run command. Cool. So that's all done. And the next thing I can do is I'll start by just getting the first training script written down. This is again a Python script. If you're not used to, if you're not using Python, you don't need to understand what this script precisely does, but it takes stochastic gradient descent classifier, 10 iterations, and trains it on the training data. It then takes the trained model and it dumps it as a joblib object. This is what this line here does. So this helps me to get access to the trained classifier also outside of a Python session, because I then have a joblib object that is a trained machine learning classifier that I can apply to all data that I would later want to. I'm saving that. And then I'm also making sure that I have a script that evaluates my classifier later on. And this script loads the joblib object that is my model and applies it to the validation data, computes the accuracy, and then prints the accuracy to the terminal, and also saves them in a file, in a JSON file, accuracy.json. I'm also saving this one, and I'm also again attaching a version tag for me to later identify this. Now the first containers run command that I'm doing is I will just execute my training script. This will run the first script that I have, or the training script that I've just added. And this is just me in my machine learning workflow in the first step, seeing how far I get with what I have initially written up. And I can see already, oh, there's a convergence warning. That's not ideal. Let's see how well this model evaluates. So I'm going to run the evaluation script. So that it tests the trained classifier. And I can see, well, okay, that accuracy is not super great. And I also got the convergence warning. So let's start to modify a script to improve the performance. What I'm doing here is I'm replacing the number of iterations. I'm increasing them from 10 to 100. I'm doing this with a stream editor. You can also do it in an editor if you want to. So here's just the git diff of what has changed. Instead of 10 iterations, my classifier takes 100. I'm saving that change. And then I will make sure to rerun the classification and also the evaluation. And this is where I'm specifying more than a single run command, but I'm actually supplying a range of commit identifiers here. You can see that I'm using the commit tag ready for analysis that I've created prior to training the model for the first time, and the tag that I have attached after evaluation and changing the number of iterations. I'm using tags here because that's the easiest way to do it without looking up hashes, but you can also just copy and paste commit hashes to identify ranges, for example, from your dataset history. So I don't need to already know which tags to append where. I can specify any range within my history. It's just that I wanted to have a very easy task in my remote control terminal. So what it does now, it takes every run record that it finds in between the two identifiers, commit identifiers I've specified, and it reruns them. It will start with the first one command that it finds, which is training. So it will retrain the classifier now with the change script. And then it will take the next one command it finds, which will be the evaluation, and it will then re-evaluate the changed model. And in this case, I can see that the accuracy has improved, which is nice. At this point in time, I already have two versions of accuracy in my history, and I have two different trained classifiers in my history that are in this model joblib file. Let's now not only change the number of iterations, but actually let's also change the classifier. So what this set or stream editing call does, it replaces the SGD classifier with a random forest classifier. Here is the precise change that has been introduced by these two commands. So instead of importing SGD classifier, I'm importing random forest classifier, and then I'm using that one. Okay. Again, first we'll save this one, again with a version tag. And then I will try to see whether that can make a positive influence on my accuracy. Again, we'll rerun all of this, but I want to be a little bit more, I want to add another, I want to showcase another feature of the DataLad rerun command that can be also very useful in this workflow by rerunning the range of commits that I'm specifying, not in the same branch that I'm currently on, but in a different branch. In this case, I'm specifying a new branch called random forest. DataLad will create this new branch and check it out. It will be on top of the version history that I'm currently am, and it will on there recreate or rerun the run records that it finds in the history. This is useful for two different reasons. One is that it allows me to compare the models that I have trained by just comparing branches. And the second is that I can quickly change between the trained models, the model joblib files, simply by switching branches, which is an incredibly fast operation. So even if you have a really large model.joblib file, because what is placed in Git is really small, branches switching is really fast. So if I'm executing this and I want to have my trained random forest classification, I'm going to random forest branch. If I want to go back to the stochastic gradient descent, I can go back to the master branch. If I execute this, then you can see that it does the same sequence of run commands as before, but it currently does so on a different branch that I can later use to compare the results. So at the moment, we're training a random forest classifier instead of a stochastic gradient descent classifier. This will update the model joblib file that holds the trained classifier. And once that is done, we will re-evaluate this model. And now I can see, okay, here the accuracy has risen another tiny bit. If I want to get a quick difference between the previous accuracy and the one that I have gotten now, I can do this with a variety of things, but one way to do this is by using gitdiff to compare the current branch I'm on, random forest, with the master branch, in particular regarding this specified file accuracy.json. So if I do this, I can see the difference in accuracies between the two models. And if I check out the master branch again, and then take a look at the accuracy file, then I'm back to the stochastic gradient accuracy, because everything I've done with the random forest model is done in a different branch. Now, the last thing I want to tell you or show you in this workflow is the case of change data. So let's say you have an evolving input data set. For this, I'm going to go back into the input data set, and I couldn't find a nice image to add, but I'm just modifying this data set by removing an image that is inside of it. So I'm taking the input data set, the ImageNet data set, and I'm removing one file that I've used. If I then query the DataLad state of the data set, then I can see that this is a deletion, and I can save this file so that I now have evolved this input dataset's history further to where I have registered it in the analysis dataset. I can now go into the registered subdataset, so a clone of this original dataset, and run a DataLad command that is called DataLad update merge. in order to pull in the changes that come from the original dataset into my dataset clone. So if I now take a look at the Git log, then you can see that there is the initial downloading and content adding, but there's also the most recent change that I've just done, which is removing an image. And if I want to keep this change, I can stay put. If I want to instead go back to the complete state of the dataset, then I could, for example, check out this commit to be back at the originally registered state. Something that I want to draw your attention to is how a subdataset state is represented in the superdataset. So if I'm now back in the superdataset ML project and then query the dataset state, then you will see that the subdataset is modified because it changed from the previously registered version to a new version. And I can make this change transparent by simply saving it with a DataLad save command. And I'm doing that right now. And afterwards, with this changed input data, I can rerun the entire workflow that I've done. So the 3 run commits that do prepping, model training, and evaluation by specifying a range again. And this is not a workflow management tool in any sense, but I hope that this has demonstrated in a way how Git concepts and such as tags or branches can be used in conjunction with run records to get some sort of managed or workflow management like feel to such an analysis and how that can be helpful. So to summarize this little workflow with some tips and tricks for machine learning applications with DataLad, you should take a standalone input dataset to keep the input data extendable, reusable, and so forth. You can register your subdataset in precise versions, and you can update it into the newest state or to previous states if you want to. You should make sure to add software containers if you can, or if you have a complex software setup, because that aids greatly with reproducibility, and it's also helpful for yourself if you have ever to update your computer. You can share this software environment and you can preserve it. Re-executable run records can capture all of this provenance, especially if you use it in conjunction with DataLad containers and the container that you register. And if you have stuff that requires command line parameterization, a run record is also one way of capturing all of that. If you are familiar with Git workflows, then those can be very helpful elements in machine learning workflows. So while DataLad is no workflow manager, it can check out tags, it can check out branches, and you can switch easy and fast between results of different models or identify different states. And so to summarize this complete workshop on DataLad, I think the takeaway that I want to show you on why to use DataLad is that mistakes aren't forever anymore. You can version control any file regardless of how large it is, and make sure that you can interact with its history and keep track of its entire evolution. You don't need short-term memory anymore if you have run records that can be helpful for yourself in order to rerun a computation or a range of computations, and it can be helpful for others to find out what was done. You have the feature of what I call disk usage magic, where you have access to more data than your hard drive has space if you have data that is stored in a remote location. And you have wonderful collaboration and updating mechanisms that bring the collaboration mechanisms from software development into scientific analysis workflows. So Alice can share her data with Bob, and when she fixes a mistake, then she can push the fix and Bob can update to the most recent version of the data. If Bob makes a change, then Alice can also make sure to get Bob's changes, and vice versa, and vice versa, and vice versa. And lastly, the transparency is a major feature, because shared datasets keeps the history. DataLad has not only a way to make it very transparent to you what has been done and to your colleagues, but it can also help to make science more transparent and open. And you can share a data object, a research data object, with all of the provenance it needs. And if you have a project that you are pointed to by a supervisor and you are tasked with figuring out what has been done, you don't need to track down the person who has worked on that project and interrogate them at gunpoint. You can simply ask their project what was done. Cool. And with that, I want to thank you for your attention. I hope that everything was clear, but if you have any questions about the machine learning example that I've just shown you, or if you have also any questions about DataLad, then please don't hesitate, speak up, we can chat. And with that, I want to thank you all for your attention.